Go ahead.
Okay. Can you see my screen?
Yes, we can see it.
Okay, so let me know when I can start.
Oh, you can start whenever you're ready.
Okay. Hi everyone, my name is Preeti Bhandari, and today I'll be talking about this paper on correspondence between neuroevolution and gradient descent. These are the authors, and this is the reference to the paper. Now, let me first give you a brief motivation and background related to this paper. So in general, the optimization strategies used in neural network is based on gradient descent or non-gradient descent. And neuroevolution comes under the category of non-gradient descent calculations. And these optimization strategies are considered different. But this paper proves that there is some equivalence between these neuroevolution calculations and gradient descent calculations under certain constraints. And this is not a new idea. This is already established in terms of statistical physics, where we talk about Langevin equations and Monte Carlo simulations. And this paper is trying to bridge these ideas for machine learning and statistical physics. So one of the significance is that it enables use of simpler optimization methods where gradients are hard to compute. Now, I'm hoping everybody already knows what gradient descent is, but just for completeness. Gradient descent method is basically, let's say you are in some initial state and you're trying to evolve towards the local minima. So it is done using this technique where you say you have this state X and you're looking into time evolution of that state towards its local minima. That's done with some learning rate alpha, and you calculate the gradient of the loss function ux.
So there should be subscript I on the left-hand side of the equation.
Oh, yeah. Sorry.
That's fine.
This is dx.
Mhm.
Okay. So neuroevolution is different in that sense. You don't calculate gradients, but it is like Monte Carlo simulation. So you do some random changes in the system. Change here is termed as mutation in this paper. So for example, you are in some state X, and now you want to go to some new state X plus epsilon. That's called a mutation, that change. And the whole paper is based on the assumption that this mutation has to be small. So this epsilon has to be small. When this mutation is small, then there is this equivalence between neuroevolution and gradient descent. So here they have taken epsilon to be a Gaussian noise with mean zero and variance sigma square. Now, Monte Carlo is a two-step process. I'll talk about the detail in the later slides, but just briefing you here that one is you propose a step, which is this mutation, and then you accept it with the probability given by this metropolis probability. I'll talk about this in detail later. So the main idea of the paper is that if you assume your mutation size to be small, then neuroevolution behaves like gradient descent plus some noise. So they have considered two cases. One is beta less than infinity. Another is beta equal to infinity. So beta is inverse of temperature. So you can assume it as finite temperature case and zero temperature case. When beta is less than infinity, in that case, your neuroevolution leads to some, you can say gradient descent equation plus some noise. And that
Pretty
noise.
sorry. Was beta defined before? Is it anywhere? Did you say what what's beta? I understand that
Beta
you want
is.
inverse temperature, but I mean, for that you need to define some kind of ensemble, or so how do they define beta?
So basically, just a second. So what I'll
Like in neuroevolution, what is beta, right?
yes. So initially, when they consider beta is equal to less than infinity case, there they have defined beta is equal to 10 raised to power 3. So it's an arbitrary value. You can change it, but for their work, they have defined beta to be 10 raised to power 3.
To be what?
10 raised to power 3.
N to the power 3.
10, 10, 10, 1, 0, 10 to power 3.
Oh, 10 to the power. No, that's
Yes.
a numerical value. I'm saying like then where does it appear in the neuroevolution
I'll 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 discuss
algorithm?
that
Okay,
later
fine.
on. Okay.
So
Later on,
this is just results. You're saying that if
yes, yes.
beta that
This
appears
is
in
just the
neuroevolution is finite, then equation 2 is relevant.
yes,
If
yes,
beta that
yes, yes.
appears in neuroevolution is infinite, then equation 3 is relevant. Yes, that's
Exactly.
okay. Gotcha.
Exactly. From master equation, I'll explain this later on. How
Hmm.
these
Because
equations come.
Metropolis was introduced somewhere, right? You mentioned Metropolis.
Yes, yes. I'll discuss that also.
Okay, so
Yeah,
you're
it comes
saying
Yes.
from
that
the Metropolis.
Yes.
Yeah.
okay,
Yeah.
good.
Here, so here are the details, but this is just the main idea I'm telling what the paper is broadly, just the
That's
main
the
idea.
result, probably main
Yes,
result.
yeah,
Yeah.
yes. The
Mhm.
main result is that you consider two cases, beta less than infinity and beta equal to infinity, and your equations changes from 2 to 3.
Mhm.
Basically, these are the two equations they'll use to calculate the gradient descent. Okay, and then you have some noise as well. And beta is equal to infinity case, that is t is equal to 0 case. They call it clipped gradient descent. I'll tell you why it is called clipped.
Mhm.
Basically, they are not allowing delta u greater than 0 moves here at all. Only downhill moves will be allowed. So your equation also changes according to that.
Mhm.
Now, from where those equation comes, let's start with the master equation. Okay. In general, P of x, t tells you that if you have a distribution x, it's at time t, then the master equation will tell you how that distribution evolves with respect to time. So you have a gain term and a loss term here. So this is just telling you the rate at which the states are evolving. W here are your transition rates. So when I talk about Monte Carlo, as I said, is a two-step process. First, you propose a step that is given by P of E. Okay, you're saying you're moving from state X to some new state X prime, let's say. So that is a proposal, which here is given by this P of E, again, a Gaussian random number distribution. Now that move will be accepted with certain probability, which is given by this function. So if, let's say you were initially at u of x is your loss function at some state x, and now you made some, you proposed that we go to some new state x plus e. Okay, you again calculate your loss function, and then you calculate the change, delta u, the difference between them. If delta u is less than 0, you always accept that move. But if delta u is greater than 0, then also you accept it, but then you accept it with this probability exponential minus beta delta u. Okay, so when beta is less than infinity, equation 5 is used. That means you are allowing delta u greater than 0 transitions as well. But for beta equal to infinity case, the delta u greater than 0 transitions are not allowed, and that's why they are called clipped gradient descent. Okay. Now, as I said before, the whole assumption is that your mutation step should be small. Okay, so you assume your epsilon to be small. And then if I do the Taylor expansion of p x minus e comma t, it is something like this. I'm ignoring the higher order terms. Similar equation will come for w as well. And then you substitute these equations in your equation 4, you'll get something like this. And this is similar to your Fokker-Planck equation, which we use in physics, where you have some drift term and some diffusion term. So your equation 4 looks something like this. And now your AX is nothing but your gradient, how your gradient descent is evolving. And BX is just the noise term. Okay. So when you are using equation 5, that means both delta u greater than 0 and less than 0 transitions are allowed. And another assumption is that this delta u has to be small. So you cannot allow large changes. So these are the two assumptions here. One, that mutation has to be small, and hence delta u should also be small. in that case, your gradient descent equation looks something like this. So previously you had minus alpha del u by del xi. Now your learning rate is dependent on beta and sigmas when beta is less than 0. And this is your noise term. But when beta is equal to infinity, in that case, your gradient descent equation looks something like this. So now your learning rate is something like sigma upon under root 2 pi. So that also varies and your noise also becomes less. And because, as I said before, delta U greater than 0 transitions are not allowed, they call it clipped gradient descent. Okay. Now the numerical setup is that they are trying to, this is one of the general examples they've considered, that they try to train their neural network with this function. Okay. And now the first case they took is, they call it a shallow network at beta is equal to infinity. They've also done it for beta less than infinity. I'll show later on. So here the total number of parameters are 90 and they initialize their weight with these values. Okay. And then they did something called deep network. So they wanted to show that the neural network architecture is not important. You can have any architecture as far as the above constraints are followed, that is small mutation, the equivalence hold for any neural network architecture. So in deep neural network architecture, the parameters are high, and this is a fully connected network. And so
let me
first,
try to understand. So for each of those two cases, deep and shallow, they kind of do
yeah.
two simulation. One is gradient descent, and the other one is neuroevolution.
Yes. I'll show that.
Okay.
This is what
Okay.
I'll show next. Okay, so you have a shallow network and deep network.
Right.
Now you define your loss function. First is gradient descent calculation. You define your loss function, and then you calculate your gradient. Now here, as I said before, this is first beta is equal to infinity case. Okay. So when your beta is equal to infinity, you have defined your gradient function aix something like this. All right. So you use this here for your gradient descent calculation. TGT is the time for the gradient descent. I'll explain these the time scales for gradient descent in neuro evolution later. But right now, this is for the gradient descent calculation at beta is equal to infinity. You define some learning rate and you calculate your gradient descent loss
So this
function.
one is very unstable, right? So when the gradient becomes small, the effective learning rate blows up, right? Because you have alpha divided by nabla u. So this whole coefficient is like effective learning rate, and so when you go, yeah, so it blows up. So it's really very unstable unless you introduce some kind of cutoff. So it's not gonna really learn. And you're saying this is a limit of zero temperature, right? When beta is equal to infinity. Okay.
Yes. Okay, then the second is you do the for the same training, you now use neuroevolution. So in neuroevolution, what you do is like we do in Monte Carlo, we initialize the network with some random weights, and corresponding to those random weights, we compute a loss function, and that's our t is equal to 0 state, which we call, let's say, a high energy state. And then we propose a move, which we call a mutation. And then that move is accepted or rejected with this probability. If it's rejected, that means we get back to the original state. Otherwise, we move forward and then we iterate the process. So now the point is, how do we define the time for, because we are using two different methods. So the mutation scale is defined as for beta is equal to infinity, sigma is lambda is some parameter and alpha is a learning rate. So this you can straight away get from here. So this was your AIX sigma upon 2 pi. So this function you equate with alpha. So you get something like this. And for beta not equal to infinity, you have this beta dependence here in your mutation scale. Okay, and what this means is that your one neuroevolution step corresponds to lambda gradient descent steps. So now the time scale is, if you say T, so T in terms of gradient descent and now T in terms of neuroevolution. So this is how you define your time. So now let's look at first result, which is for
Can I
shallow
ask you about the time scales? Another question. So to calculate the gradient descent gradient, we just do one forward pass and then we calculate the derivatives, right? And so we know in which direction to move. Now for neuroevolution, you don't calculate the derivatives, but I would say you still have to do many evaluations of the nearby states in order to estimate the gradients. And that number should depend on the number of trainable parameters. So do they have the number of trainable parameters appear in this dependence of the neuroevolution time steps and gradient descent time steps? Because I only see lambda there. And I'm not sure if lambda is proportional or is a function of the number of trainable variables.
So lambda basically, so for a particular lambda, you keep a lambda fix. And let's say, like I said, for the shallow network, you have 90 parameters, right?
So it's not related to the number of parameters.
No. So
I think my point is simple. Like you have a landscape and you're trying to move in the direction of the gradient. Well, how many times do you need to estimate the function, evaluate a function in order to know the gradient? Well, as many as there are dimensions.
so yes. So that depends. So here, the gray one is the individual trajectory. But to compare a result with the gradient, you have to do some averaging. So here, for example, there are 100 independent trajectories, and then they take the average of that, and then that is compared with.
Oh, okay. So then each one of them may perform really bad.
So if you look at the gray ones, they have just shown 25 of them. So
Yeah,
each one is
right.
plus and minus. So they're going up and below the trajectory of your gradient descent. But on an average, when you take the average of all of them, that is given by this green function.
Yeah, but I think that should be incorporated in the time scale. I would think, because if you really want to compare the two algorithms, the two trajectories, then you really need to have more of the neuroevolution like evaluation of the loss in order to equate it to the same steps in the gradient descent. But I understand what you're doing. Yes, thank you.
Okay. So here, for example, they've out of 90, they've just shown 4 different weights. And you can see their evolution with time. And the gray ones here are individual, independent trajectories. Green one is their average, and their average is compared with gradient descent. And you can see that the two are equivalent, but the lambda here is very small. Okay, so for a particular lambda which is small, that is mutation step is small, the two methods are equivalent. In this figure, they are showing all the 90 weights, but at a particular time. So here time is fixed, and they're showing that all the weights, how all the weights are at a particular time. And then finally, they show how the loss function goes as a function of time. And again, the average evolution and gradient, they show similar behavior.
But so are you saying that
Yeah.
the weights for two algorithms are the same in two algorithms?
Yes.
Well, that's also
The
strange
point.
because usually with the neural networks, deep or shallow, you have many solutions. And even if
No,
you
this is just for shallow case. For the deep case, it will be different.
okay,
This
even
is
for the shallow case, you may have many different solutions, and then just running the same algorithm twice with different random seed will just give you different weights. I don't know, maybe this problem is really simple and then it always converges to
yeah.
the same set of weights, but usually you cannot, like, by eyeballing on the weights, tell that the two algorithms are doing the same thing because they still have stochasticity in there.
Yeah, but that's what their argument is in the paper also. They say that if the two methods are same, then the neural network produced by the two networks should also be the same.
Well, if there is no stochasticity, right? So maybe they're not using stochastic gradient descent, they're using gradient descent.
Yeah, they are using gradient descent.
But then the other method, the neuroevolution method, is intrinsically stochastic. So you would not want, you may not end up in the same solution. So so I don't know. Maybe this problem is just so simple. There is only one solution to it, but in general, you wouldn't have that, even for shallow networks. So, okay, good, thanks.
So this is now for the shallow network only, beta is equal to infinity. But here I showed result for same lambda. So your mutation scale was same everywhere. Here you have varied your mutation scale. So basically, as you increase your mutation scale, you can see that the equivalence starts breaking. I mean, and this can be quantified with this parameter delta, which is telling the difference between the two weights. And when your mutation scale is very small, which is 1 by lambda, you can say that the equivalence holds for much longer time. And as you decrease your lambda, this equivalence starts breaking. Okay. Now this is for deep network. You'll see similar results that for a very small mutation step, green and the average evolution and gradient descent approximately the same, which can be seen from this loss function data as well. But as you go to higher mutation step, then the equivalence break. And if this function is behaving similarly for the two methods, that means the convergence property also remains equivalent for the two cases. And this is now for the deep neural network, again for beta, but for all 7, 4, 8, 9 parameters which were there at a particular time. And again, you can see that the equivalence is there, that from the two methods, you have approximately the same weights. And that's what they say, that the neural network produced by same methods are same, and hence the generalization properties of those networks will also be the same. This is they're showing how these function. So the red one is the target function, the sign function, which we are trying to learn. And initially at t is equal to 0, you can see that it does not follow it. But as the time progresses, both the methods follow it exactly the same way. Now beta less than infinity case, which is a finite temperature case for us. And here, because you have the beta factor, so compared to beta is equal to infinity, intrinsically your mutation step becomes slightly large because you have beta now. And the effect can be seen here. The data is much more noisy. Previously, these gray point trajectories were just around the gradient descent, but now they are fluctuating much more. But still, if your mutation step is small, there is some equivalence, but it is not as good as you have at beta is equal to infinity. So here they're showing loss function versus time. For lambda is equal to 1 is the main plot, and inside is lambda is equal to 1 by 10. So here you see there is some difference. That difference gets better if your lambda is small. And here they're showing again that same delta function, which is the difference between gradient and evolution. But they're showing that how if you increase the averaging, basically the red curve here is u average of x, and the green is u average. So if you increase the number of averagings, then your results get better. So in conclusion, they're saying that the neuroevolution behaves similar to gradient descent when your mutation scale is small. So that's important here. As the mutation scale increases, this equivalence also breaks. This correspondence between neuroevolution and gradient descent is independent of the neural structure, and they claim that it can be used for black box problems where gradients are not available. And this theory connects to seemingly unrelated optimization approach.
Perfect. Thank you.
Thank you.
Thank you, Preeti. Okay. Are there any questions, comments? Oh, you switched off the presentation
Oh,
right
sorry.
away.
Oh,
Oh, well, what if people have questions about it, right?
Sorry.
So the only question I have is about uniqueness of solution, right? So if your gradient descent has if there is a really unique solution, then yeah, all trajectories should go there, and the average trajectory should go there. But if there isn't, if there are a few solutions, and I'm sure in this regression problem that you describe, nonlinear regression problem, I'm sure there are more than one solution, and the reason why you would expect this stochastic problem to always go to the same solution isn't clear to me. So I would assume, maybe the distribution of weights will be the same in both solutions, especially because you have so many trainable parameters. So there got to be symmetries, switches between weights that will preserve the outcome of the network. So that wasn't clear. So it's not clear. Well, why would you expect it to go to the same solution?
Yeah, if you have situations where you have just one single local minima or a global minima, you know
No,
that
yeah, but I'm saying that since like like in a deep network, the bulk neurons are they have no meaning. We can switch them around and readjust the weight matrix. So there are symmetries, transformations on the weight matrix that you can do without changing what the network does. And those symmetry transformations tells us that there are more solutions. There is more than one solution. Completely equivalent solution. So there isn't a unique minima to where we will go. Because of that, I understand that gradient descent will take you to the same minima if you start with the same initial conditions. But even that, because for the weight matrix, we usually choose the random initial conditions, and so depending of how you choose the initial conditions for the weight matrix, you also end up in different minima. Equivalent, like similar in the laws, but different. And so that's why I'm not sure why would you want to demand or want the neuroevolution to be there. And then yeah, you will have and then when you do the averaging of the weights to find your average solution, you may not doing the right thing in the long run because different trajectories took you to different minima and you start averaging between them. So each of the solutions is good, but the average is horrible. And so you wouldn't want to do that. So that's not clear. It's not clear whether they're putting too much restriction on by wanting the neuroevolutions to, on average, produce a solution when you don't need to do that. So that's the only, because I don't think this problem has a unique solution. There are many, this particular problem. But anyways, this is just a comment. Are there any other questions, comments?
Yeah.
Go ahead, Diego.
Yeah, I'm just because I just implemented a contrastive Hebbian learning, and I found the exact same statement. Oh, it actually becomes gradient descent in some specific circumstances. Is gradient descent like the most fundamental underlying method behind learning in every system? Every
Well,
row gives gradient descent.
it's a linear. Like if you do the expansion, gradient is the first term, linear term, and so for the small steps, this linear term dominates. Now, if you go to larger time scales, then you have a random walk that would take over, and that's what Preeti was showing. So
that's why it shows up so often.
Yeah. So I don't think there's a deep truth or importance to the fact that in this limit of small steps, when you do optimization, you end up with gradient. The question is what to do when the steps are larger or time scales are longer. What's the right way? How to modify the gradient descent away from this tiny steps region? And then there are many ways to do this. And then, there's momentum that can be used. There is Yeah, and other ways, like, there's Adam algorithm, which is also modification of the gradient descent, which is important for longer time scales. So I think this is just because you're considering small time scales, small fluctuations, and then the most you can get is a linear, nothing else but a way. Yeah. I don't know, maybe Preeti has a different opinion, but I don't think there's really something very deep and important in this, the fact that you recover gradient descent. Okay, other questions, comments? Well, if not, thanks everyone, and thank you, Preeti. It was very nice, and I'll see everyone next week.
Bye-bye.